Alright, here's a theorem for you. Suppose that the two random variables x and y have a joint probability density function f that is positive only when x is between, say, these two marks and y is between these two marks. That is over some rectangle like this. Okay? Then x and y are independent if there exist non-negative functions g and h, such that the density function can be written as the product of these two functions of x and y, these two functions g and h. Okay. All right. So this gives us a nice way to quickly identify independent continuous random variables. For example, suppose that I have a density function that looks like this. It's some constant times x times y squared times some indicator stuff. Is this a function of x and y? Yes, because I can write it as, look, k times, here's my x, part of my x stuff, here's part of my y stuff. But be careful. All of this stuff needs to separate out too. But it does. In fact, isn't it? Can't we write this as this? Yeah. Remember, we saw this in a previous video, that the indicator function of two different statements, is equivalent to the product of the product of the two indicator functions, right? So this indicator function times this one. Okay. So indeed, yeah, I can think of all of this as some function of x, and all of this is some function of y. Okay. Yeah, and I can put the k with either one of them. So it should be true. Let's check this stuff out. First of all, let's find k so that we know exactly what this density function looks like. This joint density function looks like. So by our probability axiom number 2, I think it is. You have to have that 1 is going to be the double integral of f sub x y of x and y dy dx, or dy dx. Okay, and so this is going to be, what does this come out to be? I guess if I'm integrating with respect to x is just going from 0 to 1, y is going from 1 to 2, and it's going to be kxy squared in there times dy dx, and this is, I do the integral on the inside there. I get, first of all, that k, I guess I can pull all the way out, right? And I'll go ahead and pull the x stuff out. Okay. Now, what the heck? I'll just write the inner integral there. Y squared dy, right? Dx. Maybe sort of think of it like that. Okay, so then this is k times the integral from 0 to 1 of x, and then I've got, this will be y cubed over 3, right? From 1 to 2 dx. So this is 8/3 minus 1/3. I think it's 7/3. Is that right? I think it's 7/3 k integral from 0 to 1 of x dx. And this integral is just a half, I think, right? So the final answer, I think, is 7/3 times k over 2, or 7k over 6, which implies that since all this stuff must equal 1, k equals 6/7. Okay. Very good. Very good. And again, sometimes you see this kind of thing in modeling. Sometimes you have an idea of the behavior of the joint density function up to a constant, and so maybe you predetermine the density function form except for some scaling factor, and so then you can just solve for the scaling factor, and then you have a complete normalized density function. All right, so then let's check out independence here. I mean, we certainly x and y should be independent in this case because of that theorem. But let's test for independence anyway by getting the marginals and then trying to get the product of the marginals to see that the product of the marginals is indeed the joint density. So the marginal with respect to x is going to be the integral over the reals of the joint density function for x and y, but just with respect to y, right? Okay, so I'm going to plop in, let's see, k is 6/7, right? 6/7. Put that out there. And I have x y squared times the indicator that x is between 0 and 1 times the indicator that y is between 1 and 2, right? And all of this is with respect to y. See how I did that? I just plopped the entire joint density function into the integrand there. I'm still integrating over the entire real line, but I'm only integrating out the, so to speak, the y stuff. So x comes out, it's constant. In fact, that indicator stuff with the x in it also comes out. Okay, and I'm just left with integrate the integral y squared times the indicator that y is between 1 and 2. dy. Okay. Now, all of this stuff, of course, is just the integral from y squared from 1 to 2 dy. So that's y cubed over 3 from 1 to 2. Whoops, y cubed over 3. Carried away there. This is going to be 8/3 minus 1/3, 7/3. Right? And so this whole thing then just becomes 6/7 times x times the indicator that x is between 0 and 1 times 7/3. But look, whoops, I'm sorry. Yeah, the 3 sort of cancels with the 6 if you put a 2 there, I guess, and then the 7 goes away, and then I get 2x times the indicator that x is between 0 and 1. Okay. What about the density function for y? Or the marginal, we could say, the marginal density function for y. So that's just going to be the integral with respect to x. Oops. x, y, dy. Okay. Sorry, this is getting so sloppy here. All right. So if you work this out, you should see that you get, well, let's just do it here. This is going to be the got 6/7, right, times the integral of x y squared times the indicator of x between 0 and 1 times the indicator of y between 1 and 2, dx, right? Here I'm integrating out the x stuff. So all the y stuff can come out of the integral. All the y stuff can come out of the integral. So all of this is going to be 6/7 times y squared times the indicator function that depends on y times the integral over the reals of x times the indicator that x is between 0 and 1 dx, right? Now I'm just going to deal with this integral here. This is actually just the integral then from 0 to 1 of x dx, right? Which is x squared over 2 from 0 to 1, which is just a half. So all this is just half, and finally, and I get the final answer here is 3/7 y squared times the indicator that y is in 1 to 2. Okay. So what happens if I take the product of these two marginal density functions, f sub x of x times f sub y of y? F sub x of x was 2x times the indicator that x is in 0, 1, and then I'm going to multiply that by the density function for y, right, which was 3/7 times y squared times the indicator that y is in 1 to 2. 2 times 3 is 6. It's 6/7 there. This is 6/7 times x y squared. I could, in fact, bring these indicator functions back together like this to say it's 1 if x is between 0 and 1 and y is between 1 and 2. And then, in fact, you see that this is indeed equal to the joint density function for x and y. Now, so all of that was nothing hard about that, right? We were just sort of carrying through our test for independence. But in fact, remember that what this last theorem says is that if you can, in fact, if you have that this region for the two random variables is rectangular, basically, and if you can rewrite the density function as the product of two non-negative functions over that region, then the two variables are independent, and you can spot it then by just kind of taking a look at the joint density function, seeing if you can factor that joint density function. One other thing I want to point out, and this is really important to me, is that you using these indicator functions the way we have here keeps everything very nice and very clean. You don't have to write that it's equal to this function over this region and this thing, or in 0 otherwise, and stuff like that. So I hope you can see that this makes these indicator functions make things very nice and clean.